Alright, hi everyone. This is CHEM 1A03 Test 2 take-up for Fall 2025. So let's jump into question 1. Which base is the strongest? Well, this is pretty simple. It's just going to be the base with the lowest pKb. So that is option A. Another way you can think of this is if the pKb is lower, the Kb is going to be higher. And we know that Kb is the concentration of products over the concentration of reactants. So if the Kb is higher, that means the concentration of products is higher and the base dissociates more. So it's the strongest. All right, question 2. This is a question from the past units. So calculate the velocity associated with a carbon monoxide molecule with a wavelength of 5.3 times 10 to the negative 14 meters. So this is a question where we have to use the de Broglie wavelength, which is wavelength equals Planck's constant over mass times velocity. Now we don't know the mass, but it tells us it's a carbon monoxide molecule, and we can figure out the mass using some stoichiometry. So first we're going to find the molar mass of carbon monoxide. So carbon has a molar mass of 12 and oxygen 16, so this is going to be 28 grams per mole. Now it says a single carbon monoxide molecule, so we know we have to involve Avogadro's number some way. So we're going to write out 28 grams per mole, and we know that per mole there is 6.02 times 10 to the 23, or Avogadro's number of molecules. And when we multiply this, the moles will cancel out, and we'll be left with units of grams per molecule. So this is going to be 4.65 times 10 to the negative 23 grams. And just as a reminder, Avogadro's number on the McMaster standard calculator, there's a shortcut you can use, which is constant in the top right corner, 24. So you can just do that and it'll give you Avogadro's number. Now, we have this in grams per molecule, but de Broglie's formula actually requires it to be in kilograms. So I'm just going to convert this by dividing by 1,000. So it will be 10 to the negative 26 kilograms. And now we have everything we need to plug it into our formula. So we know the wavelength, so that's going to be lambda. Planck's constant, which as another reminder is going to be constant 0.6 on your calculator. The mass we just found. And we're looking for the velocity. So once we calculate this out, you should get as your velocity 2.7 times 10 to the 5. It might be something more like 2.6 something, but it's the closest to option A. And this is meters per second squared. Okay, moving on to question 3. What is the molecular geometry of the BrF4- anion? So we're going to draw the Lewis structure for this. So how to start is you want to add up all of the electrons in this species. So you can use the periodic table to find out how many there are. So I know that bromine, I'm just going to erase this. So bromine is in group 7. So I know that it has 7 valence electrons. And so is fluorine. So I have 4 fluorine, so I'm going to multiply that by 4. And it does have a charge of -1, so I'm going to add 1 more electron. And when you add this up, this should give you 36. So now what you do is you're going to place the central atom, and then the fluorines are going to go around it. Remember that the least electronegative atom goes in the middle, but this one's pretty obvious. That's going to be bromine in the middle. So I've connected these all with a bond, and now I'm going to subtract that bond. So each bond is 2 electrons, so I have 4 bonds, so that'll be 8 electrons. So I'm going to subtract 8, and I have 28 electrons left. I'm going to put those remainders around the fluorine as lone pairs. So now I have placed, how many lone pairs? That is 6 per fluorine, so 24. So I'm going to minus 24, and I have 4 more left, and I have nowhere else to put them. I have to put them as lone pairs on the bromine. And as a reminder, bromine is below period 3. It's in period 4, so it can have an expanded octet. So now I'm going to calculate the formal charges to make sure I've done this correctly. So as a reminder, formal charge is the number of electrons that are in the regular element minus the number of bonds minus number of lone pairs. So for fluorine, for example, we have 7 electrons originally. They each have one bond, and they have 6 lone pairs around them. That's going to give me a formal charge of 0. And for bromine, it's also 7 minus 4 bonds minus 4 for the 2 lone pairs. And I get -1, and that makes sense because the anion has a negative charge. So I'm going to put that here. And what is the molecular geometry of this? This is square planar. You can kind of think of this because the 2 lone pairs are on opposite sides, and then the fluorines will form a square around the bromine. Alright, which statement about the SeO3 2- anion is true? So, these options are all sort of relating to the structure of it, so I'm going to draw the Lewis structure just to make things easier. So it's the same as before. So we're going to add up all of the electrons. So selenium is in group 6, so it has 6 valence electrons. So does oxygen, and there's 3 oxygens, and I'm going to add the 2 for the 2- charge. So this is going to give 26. And now I'm going to connect it. Remember that oxygen is always going to be on the outside. So I'm going to subtract. I have 6 electrons right now involved in bonds. So I have 20 left to place. 1, 2, 3, 4, 5, 6. So I just placed, how many did I place down? 18. So I have 2 left, and I'm going to place them on the selenium. Now we're going to calculate the formal charge. So for selenium, it's going to be 6 minus 3 minus 2. So I have +1. And for the oxygens, I have 6 minus 1 minus 6, so it's -1. So I can actually form a double bond with one of the oxygens to eliminate the formal charges. And then these 2 oxygens still have a formal charge of -1. So that makes sense because our overall charge is 2-, and I have 2 negative charges. So now we have our Lewis structure. Let's go through the options. So A, on average, all oxygen atoms have some negative formal charge. So what's really important about this is it says on average. Some people might think, well, this oxygen over here has a formal charge of 0, so that can't be true, but it says on average. And the average formal charge it's like an average of all 3 oxygens. So even though this particular one doesn't have any charge on it, the average formal charge is going to be -2/3 because we have 2 negative charges, and the oxygen occurs in 3 different places. So it does have some negative formal charge, so the correct answer is A. I'll go through the other options as well. There are not 2 resonance structures, there's actually 3, because this double bond can move to the other positions as well. The molecular shape is not trigonal planar, it is a trigonal pyramidal trigonal planar will have 3 electron groups, while this one that we drew has 4. And there are not 6 electrons in bonds, we have 8 because of the double bond on one of the O's. So hopefully that makes sense. Alright, question 5. How many charge minimized resonance structures are required to describe the bonding in HPO4 2- anion? And the H is bonded to O, not to the central atom. So once again, we're going to draw the Lewis structure. So hydrogen will be 1. Phosphorus will be 5. We have 4 oxygens, each with 6, and we're going to add 2 for the 2- charge. And this will be 32. So now we know P goes in the middle. I'm going to connect it with the 4 oxygens, and we have an H, and we're told that H is bonded to an O. So I'm just going to bond it to this one. So now, how many electrons have we used up? We've used up 10. So we have 22 more left to place. So that's 22 that I've just placed. Now we're going to check the formal charges. This is 5 minus 4, and we don't have any lone pairs, so plus 1. The oxygens, I'm going to call it oxygen 1 for the ones that don't have hydrogen bonded to it. And it's going to be 6 minus 1 minus 6. So you'll get -1. And O2, I'm going to, actually I'll call this OA and OB because I don't want it to seem like oxygen gas. The OB is going to be the one with the hydrogen connected to it, and that is going to be 6 minus 2 minus 4. So that one has a formal charge of 0. So because I have phosphorus with +1 and the oxygens have -1, I can form a double bond. And if you calculate the formal charges again, the phosphorus will now be 0, and only 2 of the oxygens will have a -1 charge, which are these 2. I'm not going to go through it, but you can calculate it yourself if you like. So this is our resonance structures, and it's asking for how many charge minimized resonance structures there are. So there are 3, and the reason why is this double bond can move to this area and also this area. And very important, the O with the H bonded to it does not move when we count resonance structures. So that's going to be 3. So question 6 is asking which of the following molecules is nonpolar, and I've already drawn all 4 of the species out because I think we've already had a lot of practice with drawing Lewis structures. So just by looking at all of the Lewis diagrams, we can say that SO3 is nonpolar because all the other ones have a lone pair, so it has a dipole moment, whereas with SO3, all the oxygens are distributed equally. So question 7 is a singly charged and diamagnetic EF3- anion has a T-shaped molecular geometry. Which element below is a possible identity for E? So I think the way to go with this question is to just try all 4 options and see which one has a T-shaped molecular geometry. So I'm going to go ahead and just say that the correct answer is selenium, and I'll show you why, and I'm going to draw out the Lewis structure. So this would be SeF3-. Selenium has 6 valence electrons. Fluorine has 7, of course. So we will get 28. Now when I draw out, I'm going to connect the fluorines to it. That was 6 more electrons gone. I am going to place 22. And as you can see, it forms a T shape. I'm going to check the formal charges. It's going to be -1. fluorines will have 0. So I have a minus charge on the selenium, which matches the minus charge on the anion. And as you can see, it is a T-shape because we have 3 bonding pairs and 2 lone pairs. So question 8 is an equilibrium question. So we have a reaction over here, which I'm just going to write out. And we are going to make an ice table with this. So it tells us the equilibrium constant. It tells us all the pressures of the other species other than H2, and we need to find the equilibrium partial pressure of H2. So I'm going to make my ice table. I stands for initial, and we know that the initial pressure of methane is 2.3, H2 is 3.4, CO is 5.6, and we start off with 0 for H2 gas. So our change is going to be minus x, plus x, and plus 3x because we have a coefficient of 3 in front of the hydrogen. So our equilibrium is going to be 2.3 minus x, 3.4 minus x, 5.6 plus x, and 3x. So now we can plug this in to our equation, which is K is just going to be the partial pressures of all of the products over the partial pressures of the reactants. So that's just kind of a general formula. So we're given K. It says it's 1.8 times 10 to the negative 7. And we're going to do 3x to the power of 3. Don't forget that we need to cube this value because we have a coefficient of 3 in front. And we're going to multiply by 5.6 plus x divided by 2.3 minus x times 3.4 minus x. Now this will be a pretty complicated calculation. So what we can do is the small x approximation. It does in fact work for this question. So what that allows us to do is whenever we have plus x or minus x, we can just ignore x because we're assuming that x is so small that it will barely even affect the value that we end up with. So if we do the small x approximation, this will be 151.2 times x cubed over 7.82. If we solve for x, we will get around 2.1 times 10 to the negative 3. And it's asking for the partial pressure of H2 gas, which is represented by this at equilibrium. So we just have to multiply this x value that we got by 3, and that will give us 0.0063 bars. So it's going to be option D. Okay, question 9. Consider the industrial synthesis of ammonia, which is characterized by the following exothermic reaction. It tells us the K value and the temperature. Which of the following stressors will have the greatest impact on maximizing the yield of the forward reaction? So let's go over the options that we have. So A is increasing the volume. So when we talk about increasing the volume, we want to look at the moles of gas on the reactants and the product side. So on the reactant side, there's 1 over here and 3 here. So we have 4 moles of gas in total on the reactant side. And then on the product side, we have 2. So if we increase the volume, Le Chatelier's principle means that it's going to move in the direction that's going to counteract the change. So if we increase the volume, the pressure is going to go down. So it's going to move towards the side that has the more moles of gas in order to counteract the change in volume. So it's going to move towards the reactant side in the backwards direction. So it is not going to be A. So B, increasing the temperature to 500 degrees Celsius. We were originally at 400 degrees, so we have increased the temperature. And when we talk about temperature, we need to look at whether or not the reaction is exothermic or endothermic. Here they tell us that it's exothermic. So when you raise temperature, the system is going to move in the direction of the endothermic reaction. So this forward direction is exothermic. So when we increase the temperature, the endothermic is going to be towards the reactants. So this is not going to maximize the yield of the forward reaction. Next, C, turning all of the NH3 from gas to liquid. So if we turn our NH3 gas into liquid, we are going to have 0 moles of gas, and then we're going to shift to the right direction because our Q is now 0 and our K is not 0, so we need to have more pressure on the product side. So it is going to shift towards the forward reaction to create more moles of gas. So the answer is C. Let's talk about D. Well, adding xenon to increase the total pressure will not change the partial pressure of anything in the reaction, so we're going to have no change if we add xenon. So hopefully that makes sense. And we'll move on to question 10. So we are producing ammonia for fertilizer. We know K and the temperature. This is the same as question 9, I believe. So it tells us we have initially this many moles. It's in a 2-liter vessel, 400 degrees, and it reacts. What is the value of Q, and in which direction will the reaction proceed? So once again, we need to send up an ice table for this. And it tells us the amount of moles for all of these gases, but because they're gases, we need to have these values in bars. So what we're going to do is use the equation PV equals nRT and find P for the pressure. So how do we do that? Well, P is going to be nRT divided by the volume. So now let's go through each species and calculate the pressure. So for N2 gas, the pressure is going to be, so we have 0.15 moles, R is 0.083, and temperature is 400 degrees Celsius, which you just add 273 to it, so it's 673 kelvins, and divide by the volume, which is 2 liters. So the pressure of N2 is 4.2 bars. So now we're just going to do that for the other 3 gases. So H2, we have 0.1 moles times R. The temperature is the same for all of these, and so is the volume, and we will get 2.8 bars. And then lastly, we're going to do NH3. We have 0.025 moles. And we will get 0.7 bars. So now we can fill in our ice table. So this is 4.2, 2.8, and 0.7. Now, unlike what we did with K calculations, this is asking for the value of Q, and Q is a value which is not at equilibrium, so we actually don't have to calculate the change or the equilibrium for any of these. We only care about the initial value, so we can calculate Q with only the initial values. So Q is just going to be 0.7, and we need to square this because we have a coefficient of 2 over 4.2 times 2.8 cubed because we have a coefficient of 3. So our Q value is going to be 0.0053. So it's either A or D. Now let's see if it moves towards the reactants or the products. Well, Q is, what's our K value? This is our K value. So Q is greater than K, and that means right now we have more products than reactants because the Q and the K value is products over reactants. So if our Q value is greater than the K value, it means we have more products right now than we should have at equilibrium, and it's going to move towards the reactants. So the correct answer is A. All right, question 11. Determine the total ionic equation for the reaction that occurs when aqueous solutions of lithium sulfide, so this is Li2S, lithium sulfide, and copper 2 nitrate are mixed. That's copper 2 nitrate, and these are aqueous. Very important to write states for this. And it says, so we're going to form copper sulfide as a solid and lithium nitrate. And let's check to see if this equation is balanced. I need to add a 2 in front of the lithium nitrate. And now we are ready to break up our reaction into the ions. So we're going to break up only the ones that are in aqueous state. So lithium, so it's a lithium plus ion, and I have 2, so I'm going to write 2 in front of that. Our sulfur is 2 minus, copper is 2 plus, my nitrate is NO3 minus, but then remember I have a 2 here, so I'm going to add 2 in front of that. The copper sulfide I'm keeping because it's a solid, and I'm going to break up the lithium nitrate. And I'm not going to forget about the 2 coefficient in front of that, so I'm going to add it in front of both. So now all we have to do is check which one of the options matches. So it should be, so it's not going to be C. Sulfide is S2 minus. So it's not going to be B. And we need to have the 2 where the lithium is. So this is going to be option D. All right, question 12. Which one of the following salts has the lowest molar solubility? So when we talk about the molar solubility, all of these species are solids. And it says that they're salts. And in order to find molar solubility, we're going to find X. So our equations are going to be the salt dissociating into its ions, which is Pb2 plus 2F minus. Make sure to balance the equation. And we can do ice tables for these. So our initial, because these are solids, we can just do a tick here. It's not going to have any initial because it doesn't have a concentration or a pressure. But our ions here do have concentrations, and they start off as 0. And we're going to add X and add 2X. So then at equilibrium, it's just going to be X and 2X. So now we know the KSP value, and we're going to use that to calculate X. So it's KSP equals the concentration of the products. And we don't have any reactants, so it's just going to be the concentration of the products. So KSP is 2.8 times 10 to the negative 8 X times 2X squared, because we have the coefficient of 2. And this is going to be 4x cubed. And if you solve for x, you should get 1.9 times 10 to the negative 3. And now we're just going to repeat that for the other 3 salts. And I'm not going to draw out the ice table for this, just to save space. So let's do CrF3. This is going to be Cr3 plus 3F minus. Our KSP is 6.6 times 10 to the negative 11. So for the Cr3 plus, it's going to be x. And for the 3F minus, it's going to be 3x cubed. This is 27x to the power of 4. And we should get 1.25 times 10 to the negative 3. I'm going to continue this for the remaining 2. So SR2 plus 2F minus. This is 2.8 times 10 to the negative 9. X, 2x squared. So this is 4x cubed, and x is 8.88 times 10 to the negative 4. And the very last one, this is Li plus F minus. This is just going to be x times x, so x squared. And we will get 4.2 times 10 to the negative 2. So whichever one is the lowest molar solubility is just going to be the lowest one. And it looks like it's going to be SRF2 because we have the smallest exponent here, negative 4. All right, question 13. When 1 mole of the following compounds is added to 1 liter of water, what is the strongest electrolyte? So for this, we need to use our formula sheet and look at the solubility rules. So let's start with magnesium fluoride. Let's go to the formula sheet, and we need to find out if it is going to be soluble or not. So here, I see that it corresponds to rule number 4. Fluorides are soluble except group 2 fluorides, which magnesium is in group 2. So unfortunately, this is not soluble. It's insoluble. So because this is insoluble, this is going to be quite a weak electrolyte because it's not going to dissociate into its ions as much. So it's probably not the answer. It's a weak electrolyte. So next, cesium chloride. You can look on the formula sheet once again, and this is soluble because this is a chloride and it is soluble, and it's not a group 2 and there's no exceptions for that. So all right, for cesium chloride, you're going to look on the formula sheet again. So chlorides I see are over here, and there are no exceptions for this, so we know that this is soluble. So this is going to be a pretty strong electrolyte. And what ions does it dissociate into? It's going to be Cs minus and Cl minus. Sorry, this is Cs plus because we have Cl minus. All right, sulfuric acid. This is also soluble, and this is a strong acid. So what is it going to dissociate into? It's going to be H plus and SO4 2 minus, but in order to balance this, we need to add a 2 in front of the hydrogen. And then lastly, for glucose, this is a non-electrolyte. This is pretty self-explanatory. It's not really made up of any ions, so it's a non-electrolyte. So between options B and C, which one is going to be the stronger electrolyte? Well, it's the one with more ions. So as you can see, these are all like cesium is 1 plus, chlorine is 1 minus, whereas we have 2 H plus ions and we have a 2 minus here. So because it has more charges, it's going to be the strongest electrolyte. So the answer is C, sulfuric acid. All right, let's move on to question number 14. Which statement is correct about the Bronsted-Lowry theory and the Lewis theory? So here they're asking, does acetone behave as a Bronsted-Lowry base or as a Lewis base or neither or both? So let's get our definitions in check first. So a Bronsted-Lowry base is going to be a proton acceptor, and a Lewis base is an electron donor. So now let's examine what's going on in this diagram. Let's start with the Lewis base and look at the electrons. So I see here that acetone is donating an electron pair to hydronium, and its put itself on water over here because it previously only had one lone pair, now it has two. Where did the extra one come from? It came from acetone, which donated it. So we know that this is a Lewis base. Now let's look at the protons. Well, I see here that the acetone has gained a hydrogen atom, it's gained a proton, and it came from the hydronium. So it accepted a proton, so that makes it a Bronsted-Lowry base. So it is both a Bronsted-Lowry base and a Lewis base. So the correct answer is A. All right, question 15. A 0.78 molar solution of chlorous acid is found to have a pH of 1.06. What's the Ka of chlorous acid? So we have to, of course, start with writing the chemical equation out. Chlorous acid is HClO, and we are going to mix it with water, and this is going to form ClO minus plus hydronium H3O plus. And now we need to set up an ice table once again. So it tells us that the chlorous acid is in 0.78 molar solution. So we're going to write that there. Water, as we know, doesn't have anything, so just put dashes. And the ClO minus and hydronium starts off as 0. And then at equilibrium, it's going to be minus x, and plus x. And then our equilibrium will be 0.78 minus x, and x. Okay, well, we actually know what x is because it tells us what the pH is. It's 1.06. So if the pH is 1.06, we can figure out the concentration of hydronium ions, which is simply going to be 10 to the negative 1.06. And remember, if we want to go the other way, it's the pH is going to be negative log of H3O plus concentration, just as a refresher. So the concentration of hydronium is going to be 0.087. So that's our X value. And now we actually can figure out what the equilibrium is for chlorous acid. It's going to be just 0.78 minus 0.087, which is going to give us 0.693. So now we actually know all of the equilibrium values. These are just 0.0878. And now we have everything we need to calculate the Ka of chlorous acid. So it's just going to be 0.087 squared, because we have two of them, divided by 0.693. And this will give us 0.0109, which is just 1.1 times 10 to the negative 2, which is option D. All right, we have another calculation problem. What is the pH of a 1.2 molar solution of CH3NH3I? So let's begin by writing the chemical equations once again. This is a little bit more complicated, so we actually have a first equation. This dissociates into CH3NH3 plus I minus. And then we actually have a second step. We're going to have this cation is going to react with water and form CH3 NH2 plus H3O plus. All right, so that is our proper equation. And now we're going to do another ice table. And we know that the solution is 1.2 molar. So it's going to be here. Remember that that is the concentration of our original substance, but it's also the same because it dissociates and it has equal coefficients. So it's just going to be 1.2 once again. And this is going to be minus x. These are 0 initially, plus x, And what we need to do is find the X value, which is going to be the concentration of hydronium, and we can use that to find the pH. So it tells us that the pKb of CH3NH2, which is this over here, is 3.36, and we can use that to find the concentration, or sorry, the Kb value of the reaction. So because this is actually an acidic solution with hydronium in it, we need to do 14 minus 3.36, and this is the pKa value, which is what we're looking for, and this is 10.64. And now in order to find the Ka value, it's 10 to the negative 10.64, which will give us 2.29 times 10 to the negative 11. So that's the Kb, or sorry, the Ka value of this reaction. And now we can just solve for x like we've done many times before. So 2.29 times 10 to the negative 11 is x squared over 1.2 minus x. I'm going to bring the denominator over and expand. And I've moved the x squared to the left-hand side. And you can just use your McMaster standard calculator to actually calculate the x values with the function that it has on there. If you don't know it, it's on the lecture slides. And our x value is 5.244 times 10 to the negative 6. So that's x, which is also the concentration of H3O plus. So to find pH, we have to take the negative log of the concentration, which is 5.28. So it's option B. All right, question number 17. This is a very interesting one. It's one of my favorite questions on this exam. So at 40 degrees Celsius, the Kw is 2.92 times 10 to the negative 14. As a reminder, regularly the Kw value is 1 times 10 to the negative 14. But we have it a bit different here. Which statement is false? So the way to go with this question is to find out what the pH of the water is in this particular scenario, which is going to be negative log of 2.92 times 10 to the negative 14. And you will find that it is 6.77. So regularly, distilled water is neutral, and the neutral pH is 7. But in this case, 6.77 is considered neutral. Okay, so let's go through the options. Which one is false? Well, it's going to be C. The pH of some solution is not considered neutral in this scenario. It's 6.77. So A is correct because distilled water is always neutral. A pH of 6.85 is considered basic. This is greater than our calculated value. So yes, it is basic. And option D, a pH 6 solution is considered acidic. This is also true because it is less than 6.77, so it's acidic. So the false statement here is option C. All right, question number 18. Rank the species below from least acidic to most acidic. The H is bonded to the O, not to the central atom. So here I'm looking at all of our species, and I'm noticing that we have one with an extra oxygen. So HSO4 has 4 oxygens and the others have 3. According to our rule book, we know that if there is more oxygen atoms, that one is going to be more acidic. So I know that HSO4 minus is going to be the most acidic, so we can get rid of options C and D right off the bat. So with the remaining 2, with selenium and sulfur as the central atoms, we need to look at the inductive effect. So I'm going to do a very rough sketch over here. So this is our central atom, bonded to the O, and the H is bonded to the oxygen. And I'll do the same for sulfur. So we need to look at electronegativity here. So I'm going to go back to the formula sheet, and we know from periodic trends that electronegativity increases upwards and to the right of the periodic table. So let's look for sulfur. I see sulfur here, selenium is here, and oxygen is right above it. So oxygen is the most electronegative out of all three of these elements, then sulfur, and then selenium. So I actually got this question wrong on the midterm, and the mistake I made was looking at the electronegativity difference. So I thought that if the electronegativity difference was greater, it meant that it was going to be more acidic, but that's not true. We're not looking really at the difference. We're just seeing if electronegativity is greater or not. And the reason for that is here, oxygen is a lot more electronegative than selenium than it is with sulfur. And because sulfur has a higher electronegativity, it's going to draw electrons more towards itself. Of course, oxygen is still more electronegative, but it is a better competitor with oxygen to draw those electrons away. And that makes the H easier to break off, which will make it more acidic. So one more time, the electronegativity of sulfur is higher, and it is able to compete with oxygen for its electrons better than selenium. So it'll draw more electrons away, making the H easier to break off. So that makes H SO3 minus more acidic than with selenium as a central atom. So our correct answer is B. All right, question 19. This is a lab question. So for experiment 1, which of the following best describes the equivalence point in this titration? So an important thing to note here is that equivalence point is not the same as the endpoint of the titration. The endpoint of the titration is when you stop titrating, when the solution is very faintly pink. The equivalence point, on the other hand, is when the solution is completely neutral. And in our actual titration that we did in the experiment, we can never tell the exact equivalence point. We can only tell the end point, because when it's slightly faintly pink, it's actually a little bit more basic. And that's why we want to get it as light of a pink as possible, but it's still going to be slightly basic. So it's not the same as the endpoint. The endpoint and the equivalence point are not the same. So that means option C is not correct. When the solution of the Erlenmeyer flask is faint pink, we are at the end point, but not the equivalence point. It is still slightly basic. So next, option A is not correct, because the burette does not have to be empty in order for us to reach the equivalence point. Oftentimes we'll have leftover. We don't have to empty out the entire burette in order to reach the equivalence point. The burette always has usually an excess of the base. So that is not our answer. When the volume of NaOH equals the volume of HCl, that is not correct, because that is not necessarily our equivalence point, because they can have different concentrations. So our answer is B. When the moles of OH equals the moles of H3O+, that is going to be when we have a neutral solution and we have our equivalence point. And finally, question 20. Which of the following statements is true about how to properly document data in a laboratory notebook? This one is pretty simple. It's going to be that your data must be recorded in pen. I don't think we need much help with that one. So that brings us to the end of the test 2 take-up. I hope you guys found this very helpful. I know this second midterm was very challenging for a lot of us. So good luck studying, everyone.